Hey guys, sorry I can't be here, but I did decide I finally need to go to the doctor's. So before we get started with the actual lesson, when I was going through this packet, I noticed that the page numbers were weird on some of the pages. So I want to spend the next 34 seconds numbering the pages. So some of them are labeled, like number 1 is labeled. You're gonna have to go ahead and do page number 2. Keep going. 3's done, 4's done. The next one you have to label is causes for the seasons. That's going to be page number 5. Keep going. The back of that is 6. Keep going. 7. 8's done. This page here, this is 9. Keep going. 10. This one's 11. This one should be 12. Then you'll notice 13's done for you and 14's done. Where we were working yesterday, that page wasn't listed on there. Shape of Earth's orbit, that's 15. Keep going. 16, 17's done. 18 is partially there. Make sure you label that 18. This page is going to be 19. Then satellites is going to be 20. It's already labeled. This page, that's going to be 21. Then this page, that's ellipses and of the moon and the sun, that's going to be 22. And here's where we're going to get to something weird. Tides is already labeled. It's labeled 22, but please cross that off and do that on page 23. So tides is page 23. Then when you turn over, this one actually looks like it has 2 labels, 23 and 24. It's going to just be 24. And then if you keep going, the rest are completely normal. 25 all the way to page 34. So again, the last page should be page 34. So now that we are literally all on the same page, we just need to pick up from where we left off yesterday. So if you recall, we were on page 15. You already did the notes and we already practiced finding. Sorry, see, still sick. We already practiced finding eccentricity. Where we're going to pick up now is down here at the force of gravity. So starting there, let me get to there on the screen. The force of gravity. So hopefully you know that gravity is an invisible force of attraction. So everything has gravity. Even you have gravity. I have gravity. Everything that has mass will have gravity. But if you notice, none of you are being pulled towards each other. We are all being pulled down to the earth. And that's because gravity depends on 2 things, mass and distance. So all of us, our masses are nothing compared to the mass of the earth. So that's why we are being pulled down towards the earth and not towards each other. But then, if you think about it, the sun is way bigger than the earth, and we're not being pulled towards the surface of the sun. And that's because the sun is much farther away and we're much closer to the earth. So the gravity does depend on both mass and distance, and one can kind of outweigh the other. And then just to sum it up, the larger the mass, the greater the gravitational attraction. And on the same note, the closer the objects are together, the greater the gravitational attraction. Now, gravity, how strong the gravity is actually going to control the speed of the planet. So it's kind of like the pull towards the sun is going to control how fast the planet moves. And I'd actually like to add that to the top here of page 16. We're actually not going to do the notes that are here, but I do want to add a bullet right up here. And that bullet at the top of this page is going to say, let me get it in focus. The closer the planet is to the sun, the closer the planet is to the sun, the faster it goes, or the faster it moves. So going back to that diagram that we were using yesterday to calculate eccentricity, remember the Earth does not revolve around the sun in a perfect circle. The Earth revolves around the sun in a slightly oval shape, it's officially called an ellipse. And in that ellipse, one of the foci will be the sun. The other one's an imaginary dot in space, but one of them is the sun. Here I represent it with a star. So you can easily see on this shape that if the Earth was over here, that's a much shorter distance to the sun than if the Earth was over here. That's much longer. So when the Earth is closest to the sun, that's when the Earth will be going the fastest. And when it's farthest away, that's when it's going to be going the slowest. And back to page 16, those positions actually have vocab words that go with them because, of course, everything has to have a fancy name. The two vocab words are perihelion and aphelion. And let me get those into your notes for you. So we'll go back here. So perihelion is when the Earth is closest to the sun, and aphelion is when the Earth is farthest away from the sun. And I did say the Earth, but it can be anything that's revolving around the sun. So the other planets or some asteroids that are revolving around the sun. Aphelion is just when they're farthest from the sun, and perihelion is just when they're closest to the sun. One thing that we might want to consider is to add a second bullet to these. So when they're closest to the sun, remember that's when they're moving the fastest. And when they're away from the sun, that's when they're moving the slowest. One thing, so you do have to know these vocab words, just like all the vocab words this year. If you just say, like if the question says, when is it moving the fastest? You can say when it's closest to the sun. Just know that the regents will use these fancy words. And one way to remember which is which is aphelion begins with an A and away begins with an A. So A, I always say A for away. So aphelion is the one that's away, perihelion is the one that's the closest. So for the record, you're not going to do it now, but you are going to have homework tonight. It is going to start here on page 16. We're going to be finding some eccentricities. So you will need a ruler. If you don't have a ruler, I have printed you up some rulers. I literally stuck a ruler on the copier and hit print. So you can grab one of these if you need a ruler. I would just recommend folding it so that it looks kind of like a real ruler. And it may not be perfect, but it will get you the best answer. You can still find, using this fake ruler, the distance between the two foci and the length of the major axis. So your homework will start here on page 16. You're going to do all of page 17, all of page 18, and I'm saying all, but page 18 only has 4 questions on it, so it's not that much. And then here on page 19, First of all, you're going to stop after after question 15. And I'm also going to let you skip question 13. So you're really doing pages 16 through 19, numbers 1 through 15, skipping page 13. But in order to do some of these questions, we do have to go and learn a little bit more about the solar system. And that is on page 28. So we're going to skip ahead here to our solar system. And before we even start on our solar system, the notes, I would like you to grab your reference table. We're going to actually look at the final page that we've never looked at yet. And a couple of you asked me about this the other day, is when are we going to get to this reference table? So we're going to go to page 15 and we're going to look at the solar system data. So we talked yesterday about what's in our solar system, and you guys told me there's the sun, the planets, all their moons. We didn't talk about some of the things like asteroids and meteors that are in our solar system. But for the most part, you guys already knew what was in our solar system. Now, some of you might already know which planets go where, but you don't have to know that this year. You'll see here that this is all the sun, the planets, and they do include Earth's moon, which is kind of out of order, but I'll show you what I mean by that. So it starts with distance from the sun, and these are in millions of kilometers. So you'll notice that these numbers get bigger as you go down. So we're starting with Mercury is the closest to the sun. Neptune is the farthest away. Now, Earth's moon's a little weird. Now, you might notice they do put how far it is from the sun. So basically the same as Earth. But then they do add in here that it's 0.386 million kilometers from Earth. And they tell you it's from Earth. So these planets are listed in order from the closest to the farthest away, besides Earth's moon. It's not a planet, but they still put it in there. Then they tell you the period of revolution. Now, in case you forgot, revolution is how long the year is. It's how long it takes the planet to go around the sun. And then they also include how long it takes for the rotation. So you might want to add that that's the day. Now, these are given in days and years. This one's given in days, minutes, and seconds, and hours, sorry. And by the way, those are Earth days. So you'll notice, remember how we talked about yesterday, that it takes the Earth 365.26 days to revolve around the sun. And you can see that you don't have to memorize that. Same with the rotation, 23 hours, 56 minutes, and 4 seconds. So I know we used to call this 365, and we normally call this 24 hours, but they do give you the exact times here, so you don't have to memorize that. So you can see some of the weird stats here. Mercury, a year in Mercury is equivalent to 88 Earth days. So it takes Mercury 88 days to go around the sun. When if you look way down here at Neptune, it takes Neptune 164.8 Earth years for Neptune to revolve around the sun. So if you wanted to turn 1 on Neptune, you would be 164.8 Earth years old. It also gets a little weirder. Here is the period of rotation, which remember is a day, takes Earth 23 hours, 56 minutes, and 4 seconds. But check this out. It takes Mercury 59 Earth days for it to spin. Even weirder, 1 day on Venus is equivalent to 243 Earth days, which is even weirder because their year, how long it takes to revolve on Venus, is 224.7 days. So you'll see there that their day is actually longer than the year on Venus. Some of the rest of them, like Jupiter, only takes 9 hours and 50 minutes and 30 seconds to rotate. So their day's a lot shorter than ours. Also included on this chart is eccentricity. So remember what we did yesterday with eccentricity, the closer to 0, the more circle it is, the closer to 1, the more oval the orbit is. So you can see here, if you look through, Venus actually has the smallest eccentricity of 0.007. So it's basically round. It's very It's very, it's not out of round very much if we go back to the words from yesterday. It's practically a perfect circle. Now, Mercury has an eccentricity of 0.206. It's the highest eccentricity out of all of them. So you'll need all of that data, by the way, to do the homework. Also, what's listed on here is the diameter, so how big that planet is. So you can see that Earth, we're not the smallest, but we're not by far not the biggest. This got a pretty little guy here in Mercury, and look how ginormous Jupiter is. Now, mass is the same deal, so they're going to tell you how much it weighs, but it's weird because the units they're going to use is Earth. So you can see that Earth weighs 1 Earth. The sun weighs 333,000 Earths. That's a lot of Earths. Same with Jupiter. It's this equivalent to 317 Earths, whereas Mercury is only 0.06 of Earth. And then lastly, we've got the density here in the last column. So densities, if you remember, the density of water is 1. So you can see that these first 4 planets are much more dense than the rest of the planets. Now the moon goes kind of more with up here with Earth, remember. So these first 4 planets are very dense, and the remaining 4 planets are very low density, close to the density of water. Saturn would actually float in water. And what we're going to do now is fill in the notes about the solar system before you go ahead and get your homework done. So again, we're on page 28. It says our solar system, and then you've got this replica of the solar system. So we're going to start with terrestrial planets. Now, if you remember last chapter, we defined the word terrestrial. We compared it to ET, extraterrestrial. ET was an alien, so it was not from Earth. So if it's extraterrestrial, it's not from Earth. If it's terrestrial, it means it's from Earth. So when they say terrestrial planets, they're referring to the rocky Earth-like planets. And again, these are primarily made of silicate rocks. And if you remember from when we did silicate, or when we did rocks and minerals, silicate is just any rocks made of silicon and oxygen, which are what most of the rocks on Earth are made of. So these first 4 planets, Mercury, Venus, Earth, and Mars, so those first 4 planets are referred to as terrestrial planets. They are a lot like Earth. Remember, they had that higher density. They were all smaller. The first 4 are considered terrestrial planets. The other 4 are called Jovian planets. They're the gas giants. They're Jupiter-like. These ones are super low density, and you can guess by their name, gas giants. They're also huge. And again, remember, all that data was right on the reference table. The first 4 were super small and high density. The other 4 were super big and very low density. All right, the next bullet there, it says asteroid B. That should actually say asteroid belt. I don't know what happened to the LT or the lines for that matter. So what is the asteroid belt? Well, it is located between Mars and Jupiter and is composed of thousands of asteroids. So it's basically a bunch of broken up rocks that are right in between Mars and Jupiter. All right, now meteors and meteorites are very similar. In fact, a meteor is actually what we usually would refer to as a shooting star. If you've ever heard the saying, wish upon a shooting star, it's not really a star. It is a meteor streaking through the atmosphere. What happens is that light comes from the friction that the rock in the meteor makes when it hits the air, and because it's going so fast, that the rock actually starts to glow. So a meteor is a streak of light that occurs when a meteoroid enters the Earth's atmosphere. So then what the heck is a meteoroid or a meteorite or a meteoroid? Sorry. A meteorite is actually a meteor that reaches Earth's surface. I know often it's said that a meteor killed the dinosaurs, but it was officially a meteorite that would have killed the dinosaurs. It's when it actually hits Earth's surface and you could go and pick up the rock itself. And finally, the last thing for today is a comet. A comet is a huge, dirty ice ball that revolves around the sun. So it is just a chunk of ice that, just like the planets, goes around our sun, which is why it's considered part of our solar system. And this ice ball can actually melt a little bit when it gets close to the sun, and it will end up with this tail. It'll look like a ball with a tail on it when it's close to the sun. And you might ask, well, why doesn't it melt? And it actually might melt. Some comets do not survive their trip around the sun because when they get too close to the sun, sometimes they do melt. There are some famous comets. Probably the most famous is Halley's Comet. And Halley's Comet revolves around the sun. I'm looking it up right now. I think Halley's Comet, it says it goes around, I should know this. It appears every 75 to 79 years. The last time it was here was in 1986. So it is not scheduled to come back until around the year 2061. So we should all probably still be here to see that happen. It is one of the most famous comets. Another famous one is Hale-Bopp, sorry. Hale-Bopp, actually, if you want to Google that, there's an interesting story behind Hale-Bopp. It made a huge impact on my life because it happened right when I was about your age. It's just something that sticks out in my memory. Definitely encourage you to Google that one. Don't listen to it, but Google it. All right, on that note, that's all I wanted to get done for today. So if you guys could go ahead and get started again on your homework, which is pages 16 through 19, skipping question number 13. If you have any questions, just go ahead and message me on chat, on the Teams chat, and I can hopefully help you out from there. Thanks, guys. Hopefully I'll be back tomorrow. Bye.